All right, let's get started. So today, we started talking about this last time, but today we're going to be looking at set theory. And we're going to take a fairly simple approach to set theory, to be honest. Set theory is a pretty wide topic, and we're going to be thinking about it specifically in the context of, really in the context of logic and how that relates to probability. We're going to cover some very, the basic set operations, which are also directly tied to logical operations. I talked about that a little bit last time too. So we'll talk about unions, intersections, and complements, and what we're going to do is think about those algorithmically, implement them in Python, and even though, we're talking sets, technically we're going to be using lists and treating them like sets, okay? So keep that in mind as we go through this. There are, there's a type in Python called a set, and we'll talk about that a little bit separately from what we're going to use as set operations, set in the mathematical set sense, not in the Python set sense, although they are very, very similar in actual operation. Okay, so we'll cover unions, intersections, and complements, and hopefully we'll have time to get into the next set of slides, which is axioms of probability, and we'll see. We'll see how far we get with this today. And we'll just go forward. So as a reminder, there's this idea of a random experiment, right? And we talked about this, so I won't go too deep into this again. But a random experiment, you do something, and there's an outcome, and you're not sure what that outcome is going to be, until you do it. So, classic example, flipping a coin, right? Another example, classic in the probability sense, is rolling a die, right? You don't know what the outcome is going to be. It's going to be 1, 2, 3, 4, 5, or 6 for a 6-sided die. And you don't know what it's going to be before you do it. So there is some kind of randomness in a random experiment. It makes sense, right? It's in the name. There are outcomes that are, if you have a guaranteed outcome, we would call that a certain outcome. Maybe that's not a random experiment, right? If you're always going to get the same outcome, maybe it's not a random experiment. You don't want to think about it that way. If an outcome can't happen, right? Like you're flipping a fair coin, there's heads and tails, and you're like, well, I want to know the probability that you're going to get arm. There's no arm that you can get from a random coin flip or from a fair coin. So that would be an impossible outcome, and you wouldn't ask to know the probability of that, or that probability would be 0, obviously. So if there are certain or impossible outcomes, maybe you're not dealing with a random experiment. And we started talking about sets last time, and the easiest way to define a set is it is a collection of objects. It's a little abstract, but one of the key things here is that there are no duplicates, right? This is very important. There are no duplicates in a representation of a set. So keep that in mind. If you have a set that contains, other sets, or a set that contains all possible outcomes, let's say, we would call that the sample space. Okay. So there's a special set that we refer to as the sample space, or the universal set, or the containing set is another way to say that. And we represent that often with a capital S, or a capital U, or the omega symbol. You might see that. And again, the sample space is all potential outcomes from a random experiment. Now, you can have, let's think about this idea of a sample space, right? Let's say you flip a coin twice, and we're considering all the potential outcomes, right? You could have heads, 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 tails, tails, heads. Let's imagine that the order of this matters, and tails, tails, right? So let's say that is your sample space. You could have a subset, A, and A is strictly defined to mean A contains all elements where there's at least one tails, right? So that could be heads, tails, tails, heads, or tails, tails, right? We can see that A is a subset of S. And we would write that A is a subset, we could do that, of S. Or we might use this sort of epsilon-looking character. A is contained in S, right? It's contained by S. So we have the sample space, we have a subset, a strict subset of the sample space. A is a strict subset of the sample space in that all of these elements also exist in S. And we can see that there are also other elements. There's at least one other element in S in this case. Okay. So I've been talking about sets. Let's take a quick aside and look at the set data type just a little bit. Again, we're not going to be focusing on the set data type in Python, but we're going to look at something called the list set trick that is across languages. This is in a bunch of different languages. It's one of those things that you should know about, you should know how to do it. So let's make a list. I'm going to make some list. I'm going to call it list, and I'm going to make it a little bit bigger. So this list contains some things. Let's say it contains, I don't know, hockey and basketball and, I don't know, hockey again and sports ball, I don't know, death ball, whatever. So we can see there's a duplicate in here called hockey. And we might want to remove that duplicate. We might want to have some way of just getting rid of duplicates. Because the set data type is not allowed to have duplicates, or sets in general, of course, in the mathematical set you don't have duplicates, but the set data type in Python cannot have duplicates. Therefore, we can use a set to remove duplicates from a list. And to do that, we might just cast this list, right, to a set, like so. But this is now a set, not a list anymore, and we could just cast it back to being a list. And like so, we should have removed duplicates from it. So let's see. Let's make sure that did what we expected to do. And let's see, Python sets.py. I should probably print this list if we actually want to see it. Print the list. And we can see we don't have any duplicates in there. But what we also see is that we have not maintained the order of this, right? Like we can see that order is different. That's because sets do not have inherent order. Sets will not maintain order in some specified way, right? So you can't expect that. And, but lists are obviously ordered. Sets are unordered. Lists are ordered. So, like, if we want to think about this, this process of deduping, right? That's what we're doing here. This is, you might hear people refer to this as deduping, right? Removing duplicates. If you wanted to dedupe this in order, think about how you would do that. How would you remove duplicates from a list but maintain the order? So in this case, you would go hockey, basketball, And of course, you would not have hockey in there again, but you go straight to sports ball and then death ball. Let's put some other sports in here. I don't know, skiing. Oh gosh, I can't remember the name of that. Why can't I think of anything? How about javelin? That's fine. And then let's throw another javelin in there for fun. Okay. So I'm going to have y'all write a function that removes duplicates, but maintains the order of the list. And I'm going to give you 4 minutes to do that. This is sort of, the kind of algorithm trick, or the kind of algorithm you might be faced to run in various situations. Sometimes you do need to preserve order. Lists have order, sets do not. So you can't, you're not going to use the list set trick to do this. You're going to write a function called dedupe in order, takes a list and returns a list with the duplicates removed, but maintains the order that is already there. So let's do 4 minutes on this and go ahead and get started. right, let's just go through a solution here. So we're calling this dedupe in order. Dedupe in order, and we're going to pass in a list. All right, so simple collector pattern, we can just say deduped for our collector, and we can just look at each element in that list. So for each element in the list, if the element is not already in deduped, then we can put it in there. So deduped dot append, we can append the element, and we can just return deduped. All right. So let's see if that works. So we've got this list that we'll pass in, and we'll print the results. And let's actually print the list itself. Make sure that we've maintained order. Okay. All right. Oh, wait a minute. Do I not? What am I doing wrong there? Let's see. Oh, of course. I already deduped it once using the list set trick. I don't want to do that again. Okay, there we go. So notice hockey, basketball. Hockey, of course, we get rid of that, and we get sports ball, then death ball, then skiing, and then javelin, but only once. So that is working, and I'll put that solution and the other code in the Slack. Okay. All right. So let's continue with sets. Again, this idea of the sample space, right? Let's think about this idea of a sample space. This contains all possible outcomes of a random experiment. Let's think about a specific sample space, and that'll be for, let's say, rolling a six-sided die. Okay, so that's one pip. Again, like, I haven't said this before, but these little dots, we refer to those as pips. It's a word that you only know if you study probability, probably, or if you play dice games. So if I say pip, that's what I'm referring to, or pips. So there are either 1, 2, 3, 4, 5, or 6 pips, as it turns out. All right, so here's our sample space S. And we can think about our sample space in terms of the subsets, right? So again, a subset is something that can be contained by a containing set, okay? So let's make a subset, call it A, and A is going to have in it 1, 2, or 3. We can say that A is a member of this symbol. This is not epsilon, by the way, it's just epsilon shaped. A is a member of S, in that all of the elements that are in A are also in S. We could create another subset, and this could be, let's do 1, 2, 3, and 4. Okay. So we can now say also that A is a member of B, right? A is a member of B. Both of these are members of S. And let's make a third subset that is all the, we'll just say a rule, all the even number of pips. So this could be 2, 4, and 6. We can see here that A may be a subset of S, but A is not a subset of C. Okay? We can see that very clearly just by looking at it. And this is just that membership symbol, and I put a slash through it. So I'm not going to paste all of these in. we're going to be looking at this primarily through code, okay? And all of this can be referred to on the slides in one form or another. So one thing I'm going to point out, these capital letters, we'll tend to name a set with capital letters, S we'll reserve for the sample space, and we'll usually start at A and continue from there. So another representation of these, so we might, or how do I say this? A representation we often use with sets, I'm sure many of you are familiar with these. We use Venn diagrams, right? And we're going to go ahead and just start in on the classic set operations, which are union, intersection, difference, and complement. So let's first consider the set union. So I'm going to just start us off with set union. A Venn diagram for the set union, we have this box, and this is generally going to be our containing set. This is going to be our sample space. And then we're going to have, some subset in here. So let's say this is subset A. And let's have another subset B. If we're talking about the set union, then we're going to consider all elements that are in A and all elements that are in B, and only one. We don't want to have duplicates, right? So we might be throwing away duplicates in this area that's crossing over. And at the end of the day, we would shade in this whole thing because it's everything that's in A and also everything that's in B. So this is a way that we might represent visually the union between A and B, A or B. And so we write this as A union B. Doesn't matter if we do A union B or B union A, those are the same thing, okay? Union here, easy to remember, it looks like an upside down U, or it looks like a U without the tail, but that's just the union symbol. And that's a little bit messy what I drew there, but should be the same symbol. So A union B is the same as B union A, which makes sense, right? We don't really care about the order of the resulting elements in this union. Okay. A connection that you want to make early on is that union has a strong similarity to the logical OR, okay? And we'll sort of get into that more when we get into axioms of probability, but you want to make this connection. Union, you want to connect with OR. You want to make that connection. All right. So something to consider also is that you can have more than two events, okay? You can have more than just A unioned with B. You can also union this with C, okay? So let's say we have C in here, and if it's unioned with C, we're also going to add in that area. And we can represent this, we can just union with C. Again, the order of this doesn't matter, does it? It's all really the same as far as we're concerned. So I'm going to have you code a union function that is going to take in two lists, but we're thinking about these lists like they're sets. Don't use the set data type in Python. Don't use that. You're going to take lists as input. You're going to traverse those lists and construct the union of elements from those two lists. So I'm going to give you 4 minutes to do that. And this is just for two lists, again, not for three or more. We'll look at a way to do this for more than that, but yeah. So go ahead and code the union, code a union function that takes in two lists and returns the union of all the elements across those. Remember, no duplicates. All right, so let's code a union function. So let's make some lists to union. Let's do list 1 and do list 2. And what should we put in here? Let's do animals. Let's do rabbit, cat, dog, leech, why not? Kangaroo and squirrel. And for list 2, we'll do eagle, shark, cat, leech, and how about caracol. And let's do a third list. And I'm going to make sure that, oh, thank you VS Code for just running something because you think I want to run it. Okay. So let's do list 3. And list 3 is going to have a rabbit and an eagle and a cat and let's do platypus and nutria. And how about a manatee? Okay. All right, so this function we're going to use to union list 1 and list 2. And if you look at the union of this, it should be rabbit, cat, dog, leech, kangaroo, squirrel, eagle, shark. We're going to skip cat, skip leech, and include caracol, right? So this is going to be union. We're going to have 2 lists. We'll have list 1. I'm going to use the same names, but you know what? You know what I'm going to do here? I'm going to do A, B, and C instead, just to be a little clearer. So an easy way to do this, we can just copy list 1, all right? And start with that. So I'm going to say, I'll just call this list 1 copy. It's going to get list 1 dot copy. And, or, you know, we could say, in fact, why don't we just call this set union, because that's what we're building. And then I can just traverse the, I could say, traverse list 2, okay? So for each element in list 2, if that element is not in the set union, then let's say set union dot append that element, and that will be it. So we just return the set union at that point. And if we perform this union, so print union, we'll perform it with A and B. Oh my gosh, VS Code. Okay, let's see what that gets. So rabbit, cat, dog, leech, kangaroo, squirrel, eagle, shark, caracol. And that's in the same order. Again, order doesn't matter, but we're going to be preserving order simply because we're using lists. All right, so what if we want to union all 3 of these, A and B with C? If we want to do that, we can't just throw in a C here and expect that to work. We're actually going to need to restructure this function somewhat. And that's going to bring up something in Python that you're going to see here and there called star args, okay? And I'm just going to put this a little higher up here. Oh, you know what? Let me pass in. Let me put this in the Slack before we get into star args. There we go. So that's a solution for this set union of just 2 elements, right? If we want to union more than that, sorry, 2 sets, the union of 2 sets. If we want to union more than 2 sets, sort of all at the same time, which a union operation can union as many sets as you want. It should be able to do that. We're going to utilize a construct in Python called star args. It's called star args because in the parameter that we define, we put an asterisk in front of it, preceding it. And that acts as kind of a wild card, and it allows you to pass in as many things as you need. So I'll just make a quick example function here called star args, and we often will actually name this star, you know, like asterisk args. And I'm going to print the type of args first, and then we're going to look at each item in the thing that we pass in. So for each item in args, let's print that item. And notice I'm printing here. I'm not returning anything. I'm actually going to explicitly say I'm not returning anything. I don't need to put this. This is the same thing as if I don't put it, but I just want to be clear that this is just going to print stuff out. So in my star args here, let's pass in a cat. Let's pass in the number 72.4. Let's pass in a list that contains another list that says 1, 2, 3, and then bird, and let's pass in false. So notice I'm just arbitrarily passing stuff in this. It's this is not there's only one parameter defined, but I can pass in as many arguments as I want because I put the asterisk in front of that. We don't need to call this args, by the way. We could call it anything, but the asterisk is what makes this happen. So notice that's a tuple. This ends up packing in as a tuple. Cat 72.4, etc., etc., ends up packing in as a tuple. And I'm just printing each of these items in args in order, right? So cat 72.4, this list that contains sublist 1, 2, 3, and the item bird, and false. So we're going to use this idea to construct a union function that allows for multiple sets. And I'm going to go ahead and code this one up. I'll probably prompt y'all to code another star args function in a little bit, depending on time constraints. So I'm going to call this the union of multiple sets. Okay? So it's more than the union of two sets. It's a union for multiple sets. And I'm going to define a parameter. This is our star args right here. That is multiple sets. Okay? All right. So the set union here, we're going to start with an empty list, of course. And then I'm going to say for each list in that multiple sets that we, whatever it is we pass in here, we're going to check each of those. So we're assuming they're lists. We're not going to make this safe or anything. We're going to assume that we're only passing in lists. There's going to be at least one list, and we'll go with that. If we wanted to make this safe, we could check is instance of each of the items in multiple sets, and throw an error or return none if any of them aren't lists. But let's not worry about that. Let's keep this simple. So for each list in multiple sets, for each item in that list, we can check to see if the item is not in the set union, and we can append it if that evaluates to true. Okay? And then we can just return the set union, like so. All right, so if we want to perform a union on multiple sets with the sets that we have here, we can do that very easily by just passing in A, B, and C. So why don't we, let's just run that, and then we'll compare it to A, B, and C above. Okay? So here we've got rabbit, cat, dog, leech, kangaroo, squirrel, and then we're starting on the next one, eagle, shark. We already have cat, so we don't say that again. We already have leech, and we have caracol. Then we already have rabbit, we already have eagle, we already have cat, and then we go platypus, nutria, manatee. So we can see that that is working. This is very procedural, right? This is not, even though sets are unordered, we're starting at the first one, and we're just going down the list. And this is not very different from that prior function. Okay. So that's our first operation, union. All right. Union is like OR. We're going to think about it being very similar to the logical OR. All right. So next, we're going to consider the set intersection. So this will be the intersection. I think this is really appropriately named. I think looking at it, it looks like an intersection. So let me just draw this out. So here's our containing set S, and then we're going to have A, and we're going to have B, and we're going to think about the intersection of A and B as being only the elements that they share in common. Okay. The way that we write this is A intersect, so this upside down U. B, of course, this is the same thing as B intersect A. There's no difference there. Okay. If we were to add another, our set C in here, I want you to notice something. This is no longer an accurate representation of this intersection. We actually need to get rid of that, the coloring in there. It's reducing the space. Intersection kind of reduces the space, doesn't it? It doesn't matter how we write this exactly. In any order, this should be fine. C intersect B intersect A. But notice it's only this area right in here, this little orange hashed area, that's going to be shared. So this is our second operation. You're going to code the intersection function for 2 lists. Okay, not for 3. We'll get to that in a moment. I'm just going to have you code intersection for 2 lists. So I'll give you 3 minutes to do that. As soon as you get your code, or once we get down to 1 minute, go ahead and throw your solution in the Slack. So 3 minutes. Think about copy pasting code from your prior function and altering it. If you don't feel like you're going to have enough time to type it out, on the fly, copy paste is very often a smart thing to do when you're coding. Okay, go for it. All right, let's code this intersection function for two lists. We're going to use that same, well, I'm going to use that same A, B, and C up here. So we should be able to see this pretty easily. Okay, so we'll call this intersection. I'm just going to use the whole word, so def intersection, and we're going to pass in two lists, right? List 1 and list 2. Okay, so the set intersect is going to be a collector, and we're going to look at each item. For each item in set 1, I think I'm using the term element, I'll say that. For each element in list 1, and then we can check to see if that element is in, not element, is in list 2. If it's in there, we can say that our set intersect will collect that element, okay? Then we can just return the set intersect twice. All right, so let's test this with A and B. And see what we get. We get cat and leech. Now, is that correct? We can scroll up here and check. Cat, so rabbit is not in B, cat is, dog is not, leech is, kangaroo is not, squirrel is not, so that is indeed the intersection of A and B. All right. Okay, so let's see. I'm going to go ahead and code up, instead of having you do this breakout for the intersection from multiple sets, I'll go ahead and code that just to demonstrate how we might do that. So this is if we want to intersect A, B, and C, and what am I calling this? Union multiple sets. I'm going to call this other one intersection multiple sets, right? So intersection from multiple sets. And we're going to pass in multiple sets, and of course there's going to be like a collector here, so this will be the set intersect, and I'm going to say if I'm going to assume, okay, that args is greater than length 1, okay, so or I to be able to perform an intersection, it's going to have to be. Otherwise, we're going to return something empty. So I'm just going to throw a little bit of logic in here to take care of that. If the length of the multiple sets is greater than 1, okay, we're just making sure that there's more than one set in there. And let's just say the length of that first set, you know, why not if we're here, I might do this. The length of that is going to be greater than 0. There's at least one element in that first set that we pass in. If that's the case, well, let's traverse this. We're going to look at all the elements. Right, I'm using element. For each element in multiple sets, let's assume from the beginning that it is a member, that each element is a member. And then let's try to prove ourselves wrong, right? So for each other set in multiple sets, we don't need to look at that first one. Okay, we're going to skip the first one, and instead we're going to look at the second one to the end. So this should work with 2, for 3, for 9, for however many we want to pass in here. If the item is not in, sorry, I'm using element, not item. If the element is not in that set, then we're going to set is member to false, right? We have just shown that it's not a member, and we don't need to continue within this for loop. We can break out of it at that point, okay? All right, so for each, so let's get back to here. And then we can check if it is a member, then we want to collect it, right? We want to say set intersect dot append, and we'll append that element. Okay. So notice what we're doing here. We're checking, we're using only the elements in one of the sets, and we're comparing it to, we're checking membership in all the other sets. And if it's not a member in all the other sets, then we say, well, this is not a member, and we throw it away. Okay? Or we don't add it in this case. So at that point, we can return the set intersect, and we should be good. So what is the name of this? Intersection multiple sets. And let's print this. Let's pass in A, B, and C. So we should only see elements that are shared across all three of those. Oh, you know what? Let me see. Are there any elements shared across all three? Cat should be. Okay, there must be a small error in here. If the length of multiple sets is greater than 1, the length of multiple sets of 0 is greater than 0 for each element in... Oh, I see. For each element in just that first one. There we go. So I just want to look at that first set, A. And I think we should see a list here that just has a cat in it. And we do. Okay. So that is a more complex function, but you know, it's a good one to pick apart and make sure that you understand the meaning. All right. So that's two of our set operations down. Let's consider another operation. And really, you could make an argument that there's only one more operation that we're going to look at, but you know, I'll get to that in a second. This is the set difference, okay? So set difference. Not deference, but difference. Okay? And again, we'll show a Venn diagram of this. We've got our sample space, S. And we've got our subset A. And we've got our other subset B. Set difference is only going to apply to two sets, okay? And order matters here. We can represent this as, well, the way that we'll represent this is the difference between A minus B, right? A difference B, or B minus A, B difference A. These are two different things. These are not equivalent things, right? So let's consider first A minus B. A minus B is going to be everything that's in A that is not in B. Okay? So it would be that. That's A minus B. If we were considering B minus A, that is going to be, so let's save that. If we were considering B minus A, that is going to be everything that's in B that is not in A, right? Okay? So it doesn't make sense to think that we can do this both ways. It has to be one way or the other way. So let's, I'll leave this as B minus A. How would you do this, right? If you've got one list and, or sorry, you've got two lists and you're saying, well, list one, you want to retain all elements that are only in list one and not in list B, or sorry, list two. You know, that's it, not so different from the functions that you've already written or that we've already shown here. So I'm going to have you code the difference function for two lists. Give you 4 minutes to do that. Okay. And here, I'll go ahead and set a timer. So go ahead and code that up. Yeah. Again, borrowing code from your prior functions can really facilitate getting this to work the way that you want it to work. Okay, so we've got two lists. We are going to take the difference, let's say, of A minus B, something like that. So how would we go about doing that? We're defining this as the difference, and we've got list 1 and list 2, and let's say call this the set difference, and it'll be just a simple collector. Easy way to do this, if this is going to be list 1 minus list 2, then we can just check everything that's in list 1, right? So for each element in list 1, we can just check to see if it's in set 2. And if it's not, we can include it in the difference. So if that element is not in list 2, we can say set, just misspelling everything, set difference dot append will append that element. Okay. Then we can return the set difference. All right. So let's take a look at the difference between A and B, so A minus B in this case. Rabbit, dog, kangaroo, squirrel. Does that make sense? Let's just double check. Is rabbit in B? No. Is cat? It is, so we don't include it. Is dog? No. Is leech? Yes, it is, so we don't include it. Kangaroo is not, and squirrel is not, so rabbit, dog, kangaroo, squirrel. That looks like it works. And, you know, if you think about it, we're not going to have a difference of multiple sets. Doesn't really make sense. So we can just leave that one where it is. All right, so let's take a 6-minute break. And when we get back, we'll look at the complement, which will come up all the time. So 6 minutes. Could you write set difference in terms of union and intersect? I think I have to think about that for a second. I mean, I think of difference as being such a simple operation that... Oh, do you mean in the functions themselves? You could get the intersection between A and B and remove every element in that intersection from A. That would be a way to do it. So you could reference the prior function in that sense, yeah. So it would be, you get the set intersect of A with B, and then you just traverse that intersection and remove those elements from, say, a copy of A. You could just reduce the space like that. That would be a way to do it. Or you could check membership in the intersect either way. Okay, I'll see you all back here in 6 minutes. All right, so let's get to it. There was a question regarding writing the difference in terms of union and intersection. You could do that, but it's really the same operation. And what I was suggesting is that you could get the intersection of A with B. So it would be, let's do it like this. You could get A, say intersection A with B, and you could subtract that from A. So this would be the difference between A and the intersection of B, and that should get you the same result as that. There was a point made that if you remove the intersection from the union of A with B, then you would have two, well, essentially, if you remove the intersection from both of them, then you would have two mutually exclusive sets, and that is true. So what I was referring to when I was describing this is just this. So let's make sure that those are the same, and they are. Rabbit, dog, kangaroo, squirrel. If we take just the difference between A and B, and the difference between A with the intersection of A with B. So these are ultimately the same operation, as we can see there. So let's... Did I paste that in? I did. Okay, good. All right. So let's consider a concept that is going to come up over and over again in the next bit of time, and that is the complement. Oops. Just scroll down. So we'll look at this from the point of view of Venn diagram. So complement. We're going to have our sample space S. We're going to have A. No B this time, just A. So here's A. If we want to consider the complement of A, and there are a few different ways that you could write this. I'm going to just show you a couple ways. Often you'll see this as A, we call this A prime, A with this little, comma, A prime. Or the way that I'll usually write this is A with an overbar, if I'm just writing it down. But honestly, you could just do this, not A. So what is not A? Not A is everything that's not in A. That's all that is. So, that's the rest of our sample space. The complement of an event A, the complement of a subset A, is going to be everything that's in the sample space that's not in A. That's all that is. We'll often use the term complement to describe probabilities, right? So if you have the probability 0.25, the probability of some event is 0.25. The complement of that probability is going to be 0.75, right? So it's everything else. And for us, probabilities will never exceed 1. So if you have a probability and you're talking about the complement of that probability, you're talking about every other possibility, or every other the rest of the probability. But we'll get into that another time. For now, just consider the complement to be everything that is in the containing set that is not in, or in the sample space that is not in the subset. All right. And that probability of EV, that's just the probability of some event. If it's 0.25, then the complement of that probability is 0.75. Okay. So I'm going to have you code the complement function in a second. And the first thing I want to point out is that you need a sample space, right? You're only passing a single set, or in this case a list, into your complement function. So we need to construct a sample space. How do we do that? Well, it turns out that we have a function already that will do that for us. It is the union of multiple sets. We can use this to construct a sample space using A, B, and C. So A, B, C. And let's throw something else in there too. Let's throw in another couple animals. We'll throw in an albatross, and we'll throw in a vole. How about a vole? All right. So here we have a sample space, and if we print this, this is going to be, everything. So in this case, what I'll do is I'll paste this in with A, B, C, and the construction of that sample space, so that you have something to work with. And then I'll have you code the complement function. So remember, it's everything that is not in the input, or is not in the if it's the complement of A, it's everything that's not an A that is in the sample space. So give you 4 minutes to do that, and yeah, go ahead. Okay. So this one, it may not be entirely obvious. Let's see if anybody... Oh, looks like a few people got right to it. Yeah, I'm sorry I didn't see that message to post the multiple sets function. This union of multiple sets, it should be up further if you scroll up to it. But I'll post it again just to have it there as a reference as well. So one nice thing about this, it turns out complement is a special case of difference. And the complement operation is just the sample space, the difference between the sample space and whatever you're looking at. So we can just say def complement, and there'll be some sample space, and then I'll just call this list1 or list1 up. And we can just return the difference. So this is going to be a dependent function dependent on the difference function. We'll just return the sample space and that list, and that should work the way we want it to. So this is going to be the complement, and we'll pass in the sample space, and we'll pass in A, and we should get everything else. So eagle, shark, caracol, platypus, nutria, manatee, albatross, and bull, none of those are in A, and we can see that. Of course, you can stack these operations, right? We could, say the difference between the union, the complement of the union of A with B, for example, and that should get us everything except what's in A or B. So we can verify that by just taking a look at what's there. All right, so those are our core set operations. There are, in the slide deck for today, there are a number of other kind of breakout problems, either conceptual or building sets. We haven't done much set build. Well, we really haven't done any set building here except manually. I'm going to save that to counting until we get into counting in probability. And instead of doing those breakouts, I definitely encourage you to look through them and try to figure them out. There's also solutions in there. But instead of looking at the rest of those breakout slides for today, I'm going to jump into axioms of probability. Okay. My reason being, we can kind of get through that quickly. There are materials in there that we don't necessarily need to reference back to very much, but you do need to have some reasonable underpinning in those axioms. So let's switch over to the other slide deck, and as far as that goes, that's going to be, we're also going to switch to a different file, this axioms of probability file. So I'm going to go ahead and close that out. Delete that. And we'll look at it like this. Okay, so axioms of probability, and if you are following along in the slides, that is the other slide deck that I posted. Yeah, I'll post the sets.py code in the channel. Yep. Okay, so there are a number of laws that we're going to consider here. All right, we're not going to go deeply into all of these, or really deeply into any of them, but I do want to talk about them because I want to give you an idea of the complexity of logic. All right. So we've got this list of laws, and if you've learned these before, it was probably in the context of trying to, doing circuit design or doing formal logic or something else, where you're likely simplifying a logical operation. We're not going to do too much in the way of simplifying. If there's time, maybe I'll make a circuit diagram, but we'll see. We're going to mostly just go through these one by one. So I said this before, I alluded to this already, but I just want to more formally state this. We're going to make some sort of equivalence between certain set operators, or operations, I'll call them here, and Boolean operations. Okay, so just your logical operations. So Boolean operations. We're going to draw an equivalence between union and or, intersection and, complement and not. Okay? These are all words in Python that we use for logical operations. And without going into sort of the theoretical side of it, we can actually think of, if we really want to bend our head around it, we can think about true or false as representing some state of a set. As it turns out, we can do that. I'm not going to go into how we would do that, but there's a way that we can actually tie this back in. So true can represent a question that we've asked of a set, right? Does this set contain even values, right? So in some, like, I don't know, phenomenological sense, true has behind it in reality some kind of set upon which we're asking a question. And I think that's maybe a way that we can think of why set operations and logical operations are so similar, how they're essentially equivalent. So the first law that we'll consider is likely a familiar one to most of you, the Commutative Law. Okay. So let's say we have sets A and B, and so we have set A, and A has elements A, B, and C. And here we're just thinking about those like they're strings. And we have set B. B has elements B, C, and D. If we are going to union these, A union B, oops, not capital U, but A union B is going to be equivalent to B union A, right? It doesn't matter what order we do this in. These are going to be equivalent. A union B is just going to be A, B, C, D. B union A is just going to be A, B, C, D. Remember, order doesn't matter, so just putting them in some kind of rational order. That is easy to demonstrate in code. So let's say we have one set that is, we'll do 1, 2, 3 instead, just to be quick. And then we've got set 2. Set 2 is 2, 3, 4. If we want to demonstrate this, if we want to prove this, we can say set 1 union of set 2. We can check to see if this is the same thing as set 2 union with set 1, right? We would expect these to be the same thing. And if this prints out true, then yeah, then we're validating that belief. So let's just see. Evaluates to true. Turns out this is also true if we use intersection. Okay? So let's change that to intersection instead. And now we get true, true, right? Okay, so let's draw that parallel with the logical operations. And for our logical operations here, we're going to use A, B, and C. We'll say A is true. We'll do A, B, C, and we'll do A is true, B is false, and C is true. All right, so we can show this with saying A or B. Is that equivalent to B or A, right? And we can do the same thing as we did before and replace these ors with ands. And let's find out if those are equivalent. And they are. Those are equivalent operations. Okay? So that's the commutative property as we're going to consider it here. So union and intersection and an or are commutative operations. Now, if we're going to talk commutative, we're also going to talk associative, all right? So associative here is essentially similar to commutative, right? Except it's the grouping of our operations that matters. So let's say we have A union B union C. This is going to be the same thing if we group A with B. This is going to be the same thing as if we say A union B union C and perform that B and C union first. And you can think of it the same as A or B or C. In the logical sense, this is going to be the same as, I'll do a double equals just to be Pythonic, A or B or C, right? Those are the same. And we can replace union with intersection or with and it's going to operate in the exact same way. So let's demonstrate that. How would you demonstrate that with code? It's pretty easy to do that. Let's see, I've got set 1, set 2. Let me make a set 3 because I'll need that. So we've got set 3, and we'll make set 3. We'll put 1 in there. We'll put, I don't know, we'll put 4 in there, and we'll put 6 in there. So notice there's an element that's in set 3 that's not in set 1 or set 2. So if we want to see this with union, we would say set 1 union with set 2, and then we can union that with set 3. And even though I don't need to do this, I'm going to explicitly, sort of put those parentheses around the union of set 1 with set 2, even though in terms of our actual order of operations, it's going to be the same. And let's remove that, and instead we're going to, well, I don't need to remove that. What I need to do is do the set 3 union with set 2 first, and then I'll do set union ultimately with set 1. So, I'm just rearranging it here, as you can see. All right, so is that all equivalent? And, if you're following my pattern, of course, it's going to be equivalent. All right. So instead of union, let's perform this with intersection, and we should see both of these as being true, and we do. So how do we show this with logic? Let's see. I'm going to maintain the same structure, right? Just A is true, B is false, C is true. And this is going to be simple to put. We can say A or B or C, right? A or B is evaluated first. Is this the same as A or B or C, where those are evaluated first? B or C is evaluated first instead. That's the question, and we should see that that is true. Now, let's verify that for and it should not be surprising that that is also the case. Okay. So those are our basics. We can expand on this into some laws that are maybe not immediately intuitive. Okay. We'll start with one that is still sort of near to algebra, right? and that is the distributive property, or the distributive law for us. So the distributive property. This one is going to be a little different. So this is going to involve unions and intersections. So let's say we're unioning A with the intersection of B and C. When I write this, I don't need to explicitly write the intersection symbol. We're going to assume that intersection, right? So this would be B and C, or B intersects C. I can just put BC, and that will be intersection. But maybe I'll just leave it like this, since that's the way I've been describing it. This is going to be equivalent to A union B, which is then intersected with A union C. Notice what we're doing. We are, just like the distributive property in algebra, we're sort of passing this through, and we're saying A union with B, and then intersection A union with C. And we can, of course, switch these symbols around so that let's do A intersected with the union of B with C. And this is just going to be kind of the inversion of those symbols, right? So this will be A intersect B unioned with A intersect C. That's for sets. I'm going to go ahead and not demonstrate that with Python. Instead, I'm going to walk us through this by hand, this same idea by hand, except we're going to use ands and ors. Okay? So let's think about this. Still distributive. So the distributive property. And we're going to say A is true. I'm going to just put a T. B is false. I'm going to put an F. And C is true. And essentially what we're constructing here is we've got A or B and C, okay? Same kind of idea, and we're claiming that this is going to be equivalent to A or B and A or C. So let's actually fill these in with the Booleans themselves. So we're saying A, that's true. So we're saying true or false and true. We're claiming that this is equivalent to true or false and true or true. Let's work this out. False and true, of course, is false. True or false evaluates to true. Okay. So here's the question. Is that equivalent? So true or false, well, that evaluates to true. Skipping a step, so true. And true or true evaluates to true. True and true evaluates to true. And we can see that that's indeed what's happening there. Okay. So, we could switch these operations so it's A and B or C, and it would just be the inversion of that, right? All right. So, let's get into some weirder operations. There's an idea of something of idempotence. So the idempotent laws, if I can spell that, idempotent laws, are sort of tautology laws or redundancy laws. So if we're thinking sets, if we have A and we're going to union A with A, just reasoning that out, that's just going to be A, right? A union with A is A. And by the same token, A intersected with A well, what's the intersection of A with A? It's still A, right? Very direct. If we're thinking logic, A or A, right? True or true, well, that's just true, right? A and A, true and true is true. So we can see this with both, very clearly with both sets and logic. A related set of laws are domination laws. So, domination laws. If we have the containing set S, or as we sometimes refer to it, U for the universal set, we'll keep S as our sample space. If we have our sample space and we have a subset of the sample space, A, right? A is a subset of S. And we'll make that very clear. So A is a member of S, is a subset of S. A intersect S is going to equal A, right? The intersection of a set with its sample space is going to be that same set. Shouldn't be too surprising if that's the case. The other thing, again, these I think are all tautological. The intersection of A with what we call the null set or an empty set, which we represent in a couple of different ways. We can represent as being like this, right? Just an empty set, or we actually use the null symbol like so. This is just going to be null or empty. Okay? You intersect something with nothing, you get nothing. All right. So those are tautological. I think, we all kind of understand those, offhand. There are some other laws that are a little bit weirder. Well, I don't want to say weirder. They're not as obvious. Like, we don't see them as immediately. So there are laws that are absorption laws. And I think these can be very fascinating. They can take your logic and simplify them pretty effectively, if you have to use complex logic. So let's say you have A. If you union A with the intersection of A with B, turns out that's going to equal A. It's a little weirder than you might expect, right? A unioned with the intersection of A with B is A. And likewise, A intersected, I'll explicitly draw that, A intersected with A unioned with B is also A. I'm not going to show this with our, I'm not going to show this with sets exactly, but I will show this with logic, because I think now that we have this idea, this understanding that the set operations and logical operations are essentially the same, are analogous at least, I think it's easier to understand these from a logic perspective. So why don't we do that? All right, so from a logic perspective, again, we've got A is true, B is false, C is true, not 2, but true. And we're talking about A or B and, or sorry, A or A and B. A and B. We're saying that we're claiming that this is equivalent to A. So let's fill these in. Obviously on the right hand, this is going to be A is true. Here, we're going to say true and false. And we're going to say true or true and false, right? So if we evaluate this in order, true and true is false, and we're left with true or false. And pretty quickly we can see true or false. Well, that evaluates to true, and we can see that true is equal to true. A or A and B is going to reduce out to A. I can demonstrate that with the other pattern of this, which is just A and A or B is equal to A, but I think you get the idea here of this absorption. Another tautology, just really quick. If you union A with nothing, right, you're just going to get A. And I think You can almost think of that as A is absorbing null, but there's nothing in null anyway, so we're just going to leave it as it is. There are, let's just think of a couple more of these tautologies. If you have not null, this is going to be the sample space, okay? And if you have not sample space, this is just going to be null. If you have not A, right? We can think of A here as being a sample space. We can, A as being a set. We can think about A as being true or false. Either way is fine. I think we all understand double negatives are positive. This is just going to be A. So we call this involution. You don't need to remember that, but this is the involution law. So not something is just that thing. Here's another law that I think of as an absorption law, but it doesn't have a name. If you're ever finding yourself doing circuit design, which you probably won't, but if you do, this one comes up a whole lot. So let's say we have the intersection of A with B unioned with A intersected with not B. And I'll do an overline here for B, for not B. Okay, that means not B. This is actually going to reduce out to A. So let's demonstrate this with logic. I think it's a little nicer to see with logic. So we've got, again, A is true, B is false, and we'll say we've got A and B, and that is going to be performed on its own, and then we're ORing that with A and not B, which I'll just do with the overline like this. We're claiming this is going to be equivalent to A. Let's work that out. That's true on the right, of course. So we're going to say true and false, or true and not false. Okay, so let's work these out one at a time. Not false, of course, is true. So we get true and true over here. True and false is false, so we get false or this true and true. True and true, of course, is true. You get false or true. False or true is true. And we can see that we absorb all of this stuff and we just get the original, we get one of those original values, we get A. Okay, so all of this is actually to get us to something that you do need to know, that you do need to remember, not for the interview, but you will need to know this in the DSI. It's going to come back around. That is De Morgan's laws. So De Morgan's laws, it's two laws that apply to sets and logical operations, of course. And I'll just show them. So the first one is the union of A with B. If you take that whole thing and not it, or get the complement of it, that is going to be equivalent to not A intersected with not B. Okay? So that's the first one. Let's think about this in terms of logic. So I'm going to rewrite this. This is going to be, not A or B. And we're claiming that this is equivalent to not A and of course those go together, and not B. Okay? So let's work this out. So A or B, again, we're going to use A is true, B is false. So this is going to be not true or false. And this will be not true and not false. Okay, so let's work these out. Not false is true. Not true is false. So we've got false and true on the right. True or false is going to be true, right? So we've got not true on the left. Not true evaluates to false, and false and true evaluates to false. So that's our first De Morgan's law. And our second De Morgan's law is we've got not A intersect B, okay? This is going to be equivalent to not A unioned with not B, okay? So we'll do the same thing. We'll say A is true, B is false, and we'll rewrite this in logical form. So this is not A and B, right? We're claiming this is equivalent to not A or not B. I don't need these parentheses, but I'm putting them in just for disambiguity. Sorry. So not A is true, true and false. And then we've got not true here, or not false here. And let's just evaluate these. So not false is true. Not true is false. We've got false or true over here, which evaluates to true. True and false evaluates to false, so we get not false. Not false, of course, is true, and we can see that works, at least for logical operations. Okay. So this, we could culminate this into something that you don't necessarily need for the DSI, but I just kind of want to show you that these logical operations are, well, let's say they're out in the world and they're in a lot of different spaces. When you get into pandas data frames, you are going to have to construct, you have to reasonably think of constructing simplified versions of these kinds of logical operations. When you get into writing SQL queries, right, there are going to be ways that you construct your logic, and maybe you have to deconstruct it to make it more optimal so that you have less operations performing the same result. So in logic, if we're, let's say, designing a circuit, there are these things called gates. And gates for us are actually just logical operations, okay? So this is an AND gate. This is just a logical gate. If we put in true and true, we get out true, right? We put in true and false. This is AND, right? So we get out false. If we put in false and true, we get out, of course, false. If we put in false and false, we get out false. All right. There's an OR gate. If we have an AND gate, of course, we're going to have an OR gate. And it's similar. It's just got this curved part right there. We also have a NOT gate. It's not really a gate. It's just sort of a modifier. So let's say you have some kind of input, and then you've got some gate here. If you put a circle here, this indicates not. And kind of what this means is that we can have an AND gate where we negate the result, right? And you may have heard of this. This is called a NAND gate. And you can have a NOR gate as well. And all this is, let's say for an OR operation, you pass in true and true or false, right? True or false in here is going to evaluate to true, and then here it's going to get knotted, right? It's going to be knotted. So if it's true, then the outcome here will be false. And essentially, you can construct circuits. There's a gate that I haven't put on here called XOR. Okay, maybe I'll just allude to this since I've already gone this far. XOR looks like this. And what XOR is going to do is it's going to be true if the inputs are different, and false if the inputs are the same. So if you put in false, false, you're going to get false. Okay, you're going to get false. If you put in true, true, oops, I don't know why that's happening. Okay, let's just say that's true. True, true, you're going to get it. You're going to get false. But if you put in false, true, or true, false, you're going to get true. If you put in false, true, you're going to get true. Okay. So what can you do with all this? You can actually draw a circuit out of a logical operation. So why don't we do that? Why don't we draw, let's draw A, we'll do A or B. Let's do A or B. And we'll not that. Okay? So A or B. So here's our input A, B, and we're going to get something out of this. I'm going to not this, right? So A or B, knotted. We could make this more complex. We could AND this with the result of, let's say, B and C. And maybe we can leave that as it is, all right? So in this case, we've got B going into this first gate, right, A or B, knotted. And B is also going to go into another gate where it is ANDed with C, okay? And then the result of these is going to be ANDed. So if we have inputs for these, we can evaluate them. Let's say A is true. We'll just use the same classic inputs we've been using. B is false. C is true. So let's look at what happens when A is true here and B is false, right? So true and false, true or false is going to evaluate to true, and what we get out of here is false because we not it right there. Okay? And then C, which is true and B, which is false, so true and false, is going to evaluate to false, and we're going to get a false out here. So false and false, of course, is false. You might be wondering if we could draw a simpler circuit, and it turns out that we can. If we've got not A or B, we could do something like, well, we know De Morgan's law, right? We know that not A or B is equivalent to not A. Let's see, not A and not B, right? So this could be our operation. We could draw a simpler circuit. So in this case, we have not operations going into an AND gate in this case, right? So it would have to be, you know, it would be your call if we've got A, B, C. Let's say we not that first, and we not this. Oops. Not this. And this is just a generic gate indicating that we're going to not. And we pass that into a gate where we AND them, and we do the same thing here where we have B and C, and we pass this out to another AND gate. So these are two equivalent circuits at the end of the day. I know that's a little bit abstract. That's something that you'll probably explore more. These De Morgan's laws you'll explore more in the DSI. It's the kind of thing that people will ask you about, okay, in interviews. They'll give you a logical operation. They'll ask you to simplify it. That is not an unlikely scenario. I'm not saying it is what will happen in any interview, but when you're interviewing for jobs, they're going to test a breadth of knowledge, and you'll definitely want to commit De Morgan's laws into your studies.